And today I would like to talk about how we compute distances and how we implement them in boost geometry. So compared to other talks, I would say that's a bit lower level. So I will not talk about big data or geospatial analytics, things like that. But I hope it will make sense. So let me talk about the outline. So first, I'd like to do some introduction on what is boost geometry and what is distance, give you some examples, and then discuss about trade-offs between performance and accuracy when we compute distances. Then I would like to sum up with some discussion. Okay, so what is boost geometry is a part of Boost C++ libraries. It's header only. It's C++ 03 and conditionally C++ 11. So it heavily uses metaprogramming templates and tag dispatching. It actually contains primitives like geometries and algorithms and spatial indexes, R3. So it follows the standards of OGC, and it's currently is using by MySQL to provide the GIS. So most of the GIS, maybe all the GIS functions that you use in MySQL are calling functions from boost geometry. Okay, so if you want to get involved or see more about boost geometry, there is a documentation, there is a mailing list, and there is also all the code is open sourced on GitHub. Okay, so this will be our first example. I would like to go briefly into it. So there are some definitions, as you can see, and then at some point we defined the points. So this is the core of our geometry. So it will be double, it will be two-dimensional, and it will be geographic with degrees. So this is one instance of a point that we can create. And then we would like to create 2 points with longitude, latitude, with degrees. So the first will be in Acropolis, and the second one will be here. And then we'd like to compute the distance, just for an example. The distance would be this one, so 2,000 plus something kilometers. And the main questions that we would like to discuss today is how accurate is this result that we get, and how fast can we obtain it. Okay, so we have models of the Earth. It seems that we like these guys of that they believe that the Earth is flat. In this case, the math are very simple. So we use Pythagorean theorem, and everything is one line of code. But unfortunately, Earth is not flat. It could be a sphere. This is used in Google Maps, for example. It's widely used. But even worse, so Earth, as we know, is it's not like a sphere. So it's pressed a bit on the pole. So a better model is the ellipsoid. So this is, as far as I know, so is the state of the art in when you are doing GIS. And if you want to be more involved, you could also have heights and mountains and oceans. And yes, this is used in geophysics. So for now, what we are doing is the third bullet. So we treat the Earth as a flattened ellipsoid, so as an ellipsoid of revolution. And we like to do computations there. And in order to do this, we could use spherical computation or even flat computation, Euclidean geometry. And we'd like to see if we do this kind of computation, what the accuracy compared to the accurate ellipsoidal computations that we have on these models. Okay, this is what I'm going to talk about. So, okay, these systems are In boost geometry, we have types for them. They're quite simple types. So it's one for Cartesian, one for the sphere, and one for the ellipsoid. And okay, then when we compute, this is just a definition of geodesic. So it's the shortest path between two pair of points. This is the distance that we'd like to compute. So if we are on the flat, the shortest distance between 2 points is just a straight line. On the sphere, the shortest distance is a great circle. So you get this by cutting with your sphere with a hyperplane. So it's also easy. It's trigonometric equations. But if we have an ellipsoid, then the geodesic is not a closed curve. It's something like this that goes around the Earth. And this blue line is the shortest path. So if you have 2 points, we want to compute the distance of this blue line. Okay. Yes, if you see a map like a Mercator projector, this is the map that you probably had on your school or you see on a public space. So you know that a straight line is not the shortest distance, of course. So if you travel from Seattle to London by an aeroplane, you will see the GPS will go closer to the North Pole. So it's just for... okay, so connected to the previous case, these are the math more or less just to see the formulas and have an idea of the complexity of this computation. So if we are in flat, it's okay, primary school probably. Then for the sphere, we did it on I don't know, maybe high school. These are just trigonometric equations. And when we want to do the ellipsoidal thing, it's some integrals that we have to approximate them. So you can see the difference, even virtually, you can see the difference in the complexity of these methods just by looking at the math. I'm not continuing with math. I just switching to computations now and algorithms. So this is a set of algorithms or methods that we would like to try and test. So this is what I found in the bibliography. If you know some other method, yes, one purpose of this talk is to take some feedback from the GIS community. Most of them are developed in 70s. So I would say that the first one, Vincenti, is the state of the art of methods that you use when you want to compute the distance on the ellipsoid. So this is what PostGIS I think is using. But then there are a series of methods like the one by Thomas, the second one, which is a series approximation of order 2. Andoyer, the third one, which is order 1. This means a bit less accurate, but faster. We'll see details. Then you can have the analog of the great circle arc by the analog of the ellipsoid is an elliptic arc. It will not be the shortest distance, but it will be an approximation, and we'll see how accurate it's going to be. And then there are methods that can project the Earth and do Euclidean computations, and then we have spherical. So like the computations they do in Google Maps, when you just click to get the distance. Okay, so I don't like that I don't give references to this, like papers or stuff, but they are all implemented in GitHub, and there are some basic references there. In the future, I hope to provide more on this. But for now, if you are curious to see how are these methods and what the references, they are on GitHub. So okay, now let me give some examples of computing distances. So I will return to the previous one. I'm in Athens and I want to travel to ULB. This is what Google Maps will give you virtually. And this is what a small amount of code that we can write in boost geometry. The difference from the previous example is that now we can parameterize our distance algorithm with a method. All the possible methods could be the list of algorithms I told you. So it's like Vincenti or flat or spheroid. Here I will use Thomas, for example. And then what I'm getting is some results for each method. The first one, we know that is the most accurate. And for example, we can see how off is the computation by Google Maps. It's, I don't know, some meters. It's not okay. It's yes, it's 3 meters. So it's 3 kilometers. So it's a big difference. All the rest are okay, more or less accurate. So this elliptic has is elliptic 0, elliptic 2, 3 is some order that you get in the series. So the larger number, the better is the accuracy, as you can also see. And the flat Earth approximation with just Pythagoras theorem is really bad for that large distances. Okay, so let me give another example, more local. So this is the ring of Brussels. So, and let's say that I want to find the closest point to this ULB. I want to find the closest point from, if I am on the ring to ULB. So that will be the red dot, virtually, more or less. Okay, and this is a sample code for computing this. So I create a point, which is the ULB. I create a polygon, which are the longitude, latitude of the Brussels polygon. And then I just ask what is the distance between these two objects. And what I'm going to get with different algorithms will be like this. So now, okay, the distance now it's much smaller. It's 3 kilometers. So all the distance are in meters here. So you can imagine that it's 3 kilometers more or less from here to, if I want to go to the Brussels ring. Yes, spherical is off by 4 meters. You see that the first 3 methods are accurate up to I don't know, centimeters, so they are very accurate. But still, even if we are inside the city, following this flat approximation, it's not very accurate. Okay, so I would like to give one more example, especially regarding this flat approximation formula. So let's say I would like to go to some more exotic places, like in Caracas. So now we are closer to equator, and by looking at the formula, I know that I will get more accurate results. So 4 kilometers in distance in Caracas we get a very good approximation with the same formula. So it's very sensitive on when you are. So if you are building an application in Venezuela, I guess you should be happy, because this is a very fast method and you'll get accurate results. Okay. So now I'll do some simple experimental analysis of these methods. It's just a starting point, so I would like to get some more consistent results than just computing Athens-Brussels distance. So the motivation is that I think it's interesting to have a function that the user says, okay, I want accuracy of, I don't know, 3 centimeters or 3 kilometers. And the system selects the fastest algorithm. So this makes sense. It's not an easy thing, because there are a lot of parameters involved. But I think it makes sense, and also the other part of motivation is that distance computation, as far as I know, it's almost everywhere. So when you want to compute nearest neighbors, nearest neighbor queries. Another interesting example is when you have, for example, GPS trajectories in some city, or even worse in Europe, and you want to see if some trajectory is similar to another trajectory. So if you have, thousands of points, then you call an algorithm of similarity. You will get, millions of distance computations probably. So it's crucial to have a fast algorithm with your desired accuracy. Okay, so this is the motivation more or less. And okay, so in order to do some tests, we use a data set that it's here on online. It consists of 500k geodesics with WGS84 ellipsoid, and it used this library, GeographicLib, with high precision. So the results that we have in this dataset are supposed to be exact. So at least they are exact up to errors in the double arithmetic. So they are very exact for our sense. And we'd like to test all these methods that are described on this data. Okay, so one test that we can have is, let's say that we have here on the x-axis we have the maximum geodesic length in kilometers, and on the y-axis we have the mean absolute error. As you can see, so here in the lower part we have Vincenti, which is the most accurate method. It's accurate up to, this is in meters, so it's I don't know, millimeters. So it's a very good accuracy up to. This is maybe the largest geodesic that you can get. So then going from the most accurate to less accurate, we have Thomas formula, which is the blue one. Then we have the elliptic formula that we treat the geodesic as a ellipse. Then it's Andoyer formula together with some elliptic variation, and then we go to spherical, and at the end the least accurate is the flat Earth approximation that gives you an accuracy which is, as you can see, you can have an error of several thousand meters, so several kilometers. Okay. Regarding the maximum absolute error, it's the things are similar, so more or less it's the picture is the same, but we have different values here. So if you want to guarantee your maximum error that you are going to get with its formulas, you could follow a graph like this, maybe a more detailed one. Okay, and the next, so this is about accuracy. We also like to compare it with performance. So this is a very simple graph about an idea of performances. So Vincenti, which is the most accurate as you can expect, is the slowest one. So this is starting from from the slowest to the fastest. We have Vincenti, and then we have Thomas, and then there is a trade-off of these elliptic formulas, and we go up to Andoyer. And then spherical is much faster, as you can see. It's 10 times faster, maybe more than Vincenti. And the flat approximation formula, it's not very good in this graph. So the previous graphs are in log scale. So here, even if it's not clear, it's maybe 2 times faster, the flat approximation formula. So some first conclusions that we can have is that Vincent is the most accurate, and it's 2 times lower than Thomas and 5 times lower than Andoyer. Something interesting here is that Vincenti, the implementation in boost geometry compared to geographic lib, which is a very detailed library that is used by PostGIS, is 2 times faster. But geographic lib is more accurate. So there is also there a trade-off between performance and accuracy. The other interesting thing is that this elliptic arc formula, which as far as I know, not very well known, gives you a trade-off between Andoyer and Thomas regarding accuracy and also speed. So it's the third curve from down. So it's between Andoyer and Thomas. And the flat Earth approximation is very, very efficient, but it's not accurate. It's very bad in accuracy. So it's only good if you are close to equator in a small city or in few kilometers. Yeah, so these are some conclusions, first conclusions we can have. So related work, this could be a building step to go to distance between any 2 geometries. As you can, I show an example of a point and a polygon. We could have distance between line strings and multi-polygons or whatever. There is also an interesting work to point clouds that snap to geometries, like a GPS point cloud that will snap into some line string. And we are also, I think it's interesting to work on similarity between geometry. So this is Hausdorff and Ferset distances between, let's say, starting from line string. So you have a line string and you want to, or you have a set of line strings in a database, and you're given a line string and you want to see what is the most similar line string on your data set. And some of them are, we propose them for Google Summer of Code projects. So this is the first one about similarities. We have one about nearly antipodal points, which is not treated correctly right now in boost geometry. And we have another project about R3 serialization. So this is the link of the details. So if you are a student and you are interested, we'll be happy to have you as an intern. And yes, that's all. Okay with that. So the question is about if we'd like to okay, yeah, so some of them could be redundant, but I think the ones I present, did you see something that was redundant?
Not really redundant, but comparable at least. For the next slide.
Okay, so Andoyer compared to one of the elliptic. Yes, maybe this makes sense, but what I lie about is that there are also some problems with corner cases. So, for example, Andoyer may have a problem in corner cases or near antipodal points, for example, and elliptic arc will have problems of points that have similar segments that have similar latitude. So it's very inaccurate in these cases. So I think it would make sense first to try to solve these problems either by fixing the 70s formulas, or have some cases that if the segment is bad for elliptic, then switch to Andoyer. And so this makes sense what you say. So in general, it will be nice to have an interface that hides all these technicalities from the user. Yes, this is the ultimate goal. Okay, so the question is regarding integration in MySQL. So everything I said here is outside of MySQL. Okay, so all the tests are in Boost Geometry with standalone library. Yes, and as far as I know, in MySQL now there is only there is Andoyer, Thomas, and Vincenti, and you also have spherical. So I don't know how you can get them, but they are there. No?
Yeah, well, geographic is Andoyer, but you can get spherical, at least, by being explicit. But,
Okay, so the first and the fourth.
Thomas and Vincenti are not there. It's quite valid if you want, but we haven't created that.
So, do you know, or what is known about computing areas and the accuracy of computing areas? Who's going to do that?
Yes, so the question is regarding areas, area computation. So we have algorithms for areas that are parameterized by distance functions. So you can, there is a generic algorithm that takes as a parameter one of these formulas. Actually, right now, as it is in Boost Geometry, it takes only Andoyer, Thomas, Vincenti, and spherical. So these are new. And compute the area. There is a GitHub page that have some examples. But as functionality is there and it's stable enough, I haven't done extensive experiments as this. But that dataset has also areas. So I guess maybe it could make sense to also compute areas. But I didn't know that users are interested in areas. So maybe, yes, if you have an application.
Use case would be for computing small areas like parcels of land or buildings. So I don't know, what the accuracy and if it matters at all from that.
Yes, I guess in buildings, even spherical or even some projections will be enough. I mean, what do you mean? Okay. The mountains and this stuff. So it's good for Belgium at least. Yes. So, but this is a very core functionality. I mean, if you want to use it to count, if you have a GPS track, I guess you can. Yes. So you can use also the altitude. Yes. Okay. So yes, this would be a nice future route. Okay. Thanks. Thanks.